Welcome to Manifested Publishers.
Hello learners, welcome to Manifested e-learning platform. I'm your chemistry teacher, Mwaniki Nyaga. Today's lesson, we are going to talk about how you can investigate energy changes during melting and boiling. Investigating energy changes during melting and boiling. In this experiment, or suppose you are to do this experiment, you'd require apparatus like 250 centimeters cubed glass beaker. You'd require a thermometer with a range of negative 10 degrees Celsius to 110 degrees Celsius. You'd require a Bunsen burner for heating. You'd require a tripod stand, a wire gauze. Those are the apparatus which you require for this experiment. The reagent is only one. You require pure ice. The procedure for this experiment would be, the first procedure would be half fill a 250 centimeters cubed glass beaker with crushed ice and record its steady temperature. So just get your crushed ice, half fill the 250 centimeters cubed glass beaker and record the temperature of that ice using a thermometer. That is our procedure number one. Number two, place the beaker containing ice on a tripod stand. So get your ice which is in the beaker now and put it on a tripod stand. And on that tripod stand, that's now where the wire gauze is. Remember again in Form 1, we talked about the wire gauze, the function being for uniform distribution of heat. So the wire gauze is just on top of the tripod stand. Then on that tripod stand, that's now where the beaker, which is half filled with ice, is on. Our procedure number 3, gently heat the beaker while stirring the ice with a thermometer. Remember, you are heating using the Bunsen burner. So the Bunsen burner is a flame which you are using to heat the beaker as you record the temperature of that ice using a thermometer. That is our procedure number 3. Then procedure number 4, you would record the temperature at 1 minute intervals. So record the temperature after every 1 minute. Let's say you have the first minute, you record the temperature, the second minute, the third minute, the fourth minute, like that. So you record the temperature at intervals of 1 minute until all this ice has melted. So until all the ice has melted. Then procedure number 5, you heat the water and record the temperature after every 1 minute until it boils. Remember, you've already melted this ice. It has now become water, which is now in liquid form. So in the procedure number 5, you are heating this water. It's now in liquid form. And you also record the temperatures after every 1 minute until this water starts boiling. Procedure number 6, you heat the boiling water for another 2 minutes. You heat the boiling water for another 2 minutes as it is still boiling to investigate whether there are some more changes in temperature you are going to realize. Then lastly, you need to record your results in a table as shown below. This is the table which you are now going to record your results after you've done the experiment. This table has time in minutes on one column and temperature, which is recorded in degrees Celsius. So time in minutes. So you have 1, 2, 3 until 15th minute. Now the temperatures, you don't have the temperatures because you're supposed now to get the temperatures from the experiment. So suppose in our first minute, we got the temperature of this ice as -10. So -10 again, because our thermometer is a range of -10 to 110 degrees Celsius. So you cannot, with that thermometer, you cannot record any temperature below -10 degrees Celsius. Then in the second minute, you have something like -5 degrees Celsius. Then the third minute, you have a 0. Then in the fourth minute, you also have a 0. In the fifth minute, this you have 9. In the sixth minute, you have like 20. In the seventh minute, you have like 34. In the eighth minute, you have 55. In the ninth minute, you have, this is 67. In the 10th minute, you have like, say, 80. 11th minute, you have 95. Then 12th minute, you have, let's say, 99. 13th minute, you have, let's say, 100. Then 14th, 100. Then 15th, 100. Suppose now those are the results we have gotten in our experiment. Our question is, draw a graph of temperature against time. So drawing a graph of temperature against time. You can use these results to draw a graph. In our case, we are going to sketch a graph with those kind of results. And the graph is temperature against time. Our y-axis, we have temperature. So this is our temperature. And the units of temperature is degrees Celsius. In our x-axis, we have time. This time is in minutes. Those units are very important. You need to include them. So in the x-axis, we have 1 minute to all the way to 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. Have 15 at the end. It is a scale, it's a sketch, it's not drawn to scale. Then the temperatures, the lowest temperature we have a -10. So if we were to extend our graph a little bit, so we'd have a 0. Then we have, let's say, -5, or let's say -10. Have 10, 20, 30, 40, 50, 60, 70, 80, 90. Then 100. So our lowest temperature was -10 at the first minute. So this is our first minute. Assume that the first minute is here. The first minute you have -10, so you expect that the temperature will be around 10. So you plot 1 against 10. So we have 1 and we have -10 on the y-axis. So our plot should be at that point. The second, we have at 2. At second minute, you have -5. So second minute and -5 is somewhere there. Then our plot should be at such kind of a point. The next point is 3. The third minute, the temperature is 0. So our plot should be somewhere there. Then the fourth minute, temperature is also 0. So the plot will be there. Then fifth, it's around 9. Then sixth, it's around 20. Somewhere like that point. Then 7, you have 34. Then 8, you have 55. Then 9, you have 67. 10, we have 80. 11, we have 95. 12, the 12th minute, we have 99. In the 13th minute, you have 100. In the 14th minute, you also have 100. And 15th, we have 100 also. So those are the plots using time and temperature. So time on the x-axis, then temperature on the y-axis. So if you are to draw a curve, then a curve will be like this. So just join the dots together. So that is a kind of a graph that you expect to obtain when you do the experiment. Suppose now we label this graph as that point A, this being point B, this is our point C, our point D, and our point E. So it looks like that, though ours is not drawn to scale. So if it was drawn to scale, again, it would be something which looks more neat compared to the one we've just done a sketch of values we've just gotten from our minds. So if you are to explain what happens between point A and B, what happens between point A, B? This is a point AB. So what happens in point AB? In our procedure, the crushed ice half fill the 250 centimeters cubed glass beaker with crushed ice and record its steady temperature. So when you recorded the steady temperature, then at that point it was -10. Temperature is -10. You now started heating this ice. When you heated this ice, then the temperature started rising. So the temperature rises. So the heat energy is now being applied on the ice. This heat energy is being converted to kinetic energy. This kinetic energy now makes the molecules of ice to vibrate more vigorously. So when they vibrate more vigorously, now there is change in position. They are able to change their position because it's now a liquid. So basically what happens, the heat energy is converted, or heat energy applied is converted to kinetic energy. So the molecules of water, they are now gaining the kinetic energy. The kinetic energy makes the molecules to vibrate more vigorously until ice melts. And again, that's why there is temperature rise. At this point, this is where you started heating. So at the heating point, you heat, so the molecules gain kinetic energy. That kinetic energy is now making the molecules of this water to start vibrating. So once they vibrate, then they vibrate even more vigorously, and that's why they steady rise in temperature between point A and point B. So that's what happens in point A, B. The second point is BC. Then at BC, you can see there is no gain in a temperature, because what happens is that the heat energy supplied is used to break the intermolecular forces of attraction holding the molecules together. So there is no gain in temperature. So no temperature gain. No temperature gain, because you can also observe at the 3rd minute, temperature is 0. At the 4th minute, the temperature is also 0. So at this point, ice melts into a liquid. So ice melts into a liquid at the melting point. So from now, this graph, you will realize that the melting point of water is now 0, that water melts at 0 degrees Celsius. Then the heat energy required to melt a given amount of a solid to a liquid is called the latent heat of fusion. So latent heat of fusion, we've said, it's the heat energy required to melt a certain amount of a solid to a liquid. The heat energy required to melt a certain amount of solid to a liquid is what you are calling the latent heat of fusion. If you melt 1 mole of a certain solid to a liquid, then that one will be called molar heat of fusion. So molar heat of fusion being the amount of heat energy the amount of heat energy required to melt 1 mole of a solid to a liquid. For example, we have ice. Ice is just water. So 1 mole of ice, the relative formula of water is like that. So 1 mole of ice will have hydrogen has a mass of 1, and there are 2 atoms of hydrogen, Cu times 2, plus oxygen has a mass of 16 grams. So when you add them together, this will be 2 plus 16, which will give you 18 grams. So 1 mole of water is 18 grams. So molar heat of fusion is the amount of heat energy which will be required to melt this 18 grams of water into a liquid, 18 grams of ice to a liquid. That is the molar heat of fusion. So that's now what is happening between point B, C. And that's why there is no gain in temperature between point B, C. Let's go to point D, E. So before DE, we have CB, CD. Then at CD, the molecules of water gain more heat energy and vibrate more vigorously. The molecules of water, because it's now a liquid, not in solid form but in liquid form right now. So the molecules of water gain more heat energy. Remember, you are still heating. It gains more heat energy and they vibrate more vigorously, leading to a steady rise. Leading to a steady rise in temperature. And that one, you can be able to see it from your graph, that at 4th minute, so the temperature is rising very steadily and all the way up to up to this point, up to 100. So from 0 and all the way up to 100, because the molecules of this water are gaining heat energy and they are vibrating more vigorously, leading to a steady rise in temperature. And our last part is part DE. Part DE. So what is happening at part DE is just like at part BC. The heat energy supplied the heat energy supplied is used to weaken the intermolecular forces further as the liquid boils. So there are intermolecular forces still in this liquid. Those forces are now weakened further as the liquid boils. The amount of heat energy required to boil a certain amount of a liquid into gas or into gaseous state, we call it latent heat of vaporization. Latent heat of vaporization, I've said again, that it's the amount of heat energy required to convert a certain amount of a liquid to a gas. The amount of heat energy required to convert a certain amount of a liquid into a gas. That is the latent heat of vaporization. If this certain amount of a liquid is 1 mole, then it would be molar heat of vaporization. Molar heat of vaporization. So the molar heat of vaporization would be the amount of heat energy required to convert 1 mole of liquid water to a gas. And 1 mole, we have said, it's 18 grams. So the amount of heat energy required to convert 18 grams of liquid water into a gas is what you're calling the molar heat of vaporization. So it is important you distinguish between those two important terms. So you have the latent heat of vaporization. You also have the latent heat of fusion. Get the difference between the two. Latent heat of fusion, heat energy required to melt a certain amount of a solid to a liquid. Then latent heat of vaporization, the amount of heat energy required to convert a certain amount of a liquid into a gas. Of course, now the molar, it is when you're dealing with 1 mole of a certain substance. Again, ensure that you remember what is happening at various regions. This is region AB. What is happening between this region, point AB, the changes which are taking place. Then point BC, the changes which are taking place. Like now in BC, you have said the heat energy supplied is used just to weaken the intermolecular forces holding the molecules together. So there is no gain of temperature. And at this point, this is now where melting is taking place. Then at point CD, we have seen again that the molecules of water gain more heat energy. When they gain more heat energy, then this heat energy is now converted to kinetic energy, and it's now making the molecules of water to vibrate even more vigorously, leading to a steady rise in temperature. That is what is happening at point CD. Lastly, it's at point DE. So the heat energy supplied again is used to weaken the intermolecular forces further as the liquid boils. You can see even after heating further for 2 minutes, there is no gain in temperature. It still remains 100. Now this shows you that the melting point of this water is, or the melting point of ice is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. Those are very important. Then ensure that you understand those terms very well. And again, you can be able to explain each and every term and what is happening between each and every region. Again, be able to draw the graph between the graph of temperature against time. And I've told you again, anytime you're told a graph of temperature against time, then temperature should be on the y-axis, then time on the x-axis. The next thing we are going to discuss will be board breaking and board formation in chemical processes, because this is a physical process. Boiling of water and melting of water is a physical process, as you said. So it's an endothermic reaction which involves gain of heat so that you're able to break down or to weaken the forces of attraction between, or to weaken the intermolecular forces which are holding those molecules together. And again, the same amount of energy required to melt a certain amount of a solid to a liquid, then that same amount of energy will be liberated or will be evolved when you convert or you're freezing this liquid into a solid. I hope you get that very clearly. I will leave you with an assignment. The assignment is define the following terms. The first term is latent. Latent heat of fusion. And the second is latent latent heat of fusion and latent heat of vaporization, as we have discussed them here. So ensure that you've done that before we meet in our next lesson. And thank you for participating and being attentive in this lesson.